All right. So electrochemistry is what we're talking about here. This chapter is all about oxidation reduction reactions. And we talked about this very briefly in first semester. Contrasts with an acid-base reaction where usually protons are transferred, right? In an oxidation reduction reaction, what is transferred? Electrons are transferred. Okay? So here's an oxidation reduction reaction. Let's figure out how the electrons get transferred in this. This is a standard redox reaction where we've got an element and a compound, making a compound and an element. We can use oxidation numbers to keep track of that. So pure elements are 0. Right? Pure, just neutral elements like magnesium, those are 0. If it's magnesium in a compound, its oxidation number is the same as its charge. So what would oxidation number be for magnesium over here? It would be 2 plus. Okay. What about the silver over here? 1. 1. And here, I'm writing them like charges. I should write them like oxidation numbers with the sign before the number. That's not a huge deal, but that's how it's done. I have to get myself back into that mode. But yeah, nitrate NO3 is a 1 minus ion. So silver is plus, and then the silver over here is 0. Okay. So you track each of those, and nitrate just stays as nitrate. That doesn't change. Okay. So we track each of the ions from one side to the other to figure out what happened. Okay. To go from 0 to plus 2, what did magnesium have to do? Had to lose 2 electrons. Oops, color there. Lost. And likewise, silver had to gain 1 electron each, okay, with the coefficient of 2. Okay. So, what did we define oxidation as? Anybody remember?
Oxidation is
Loss of electrons. Okay. Do you use something to help remember that?
Oil rig.
Oil rig. And Leo says grr. I think I told you guys about those last semester. And the funny thing is, every chemist I know uses Leo and Gur, uses the lion, and every biologist I know uses oil rig. I just thought that was funny. So still in my head, to this very day, I say Leo and Gur, just to make sure I don't get them backwards. Okay? So where was the oxidation here? Where was the oxidation here? Yep, this was the oxidation. Okay? And the silver was the reduction. Okay? Easy way to remember that is that we all know that metals get oxidized, right? Iron rusts. Okay? And metals, they start out as neutral atoms. They form positive ions. Okay? So that has to be loss of electrons. So that's an extra way of sort of double checking. Okay? So if you're starting with a pure metal like this, pure metals get oxidized. We don't make minus ions out of pure metals. Okay? So, okay, then just to make things complicated, what is the oxidizing agent here? Yeah, it is the opposite. Okay? The oxidizing agent is itself reduced. Oxidize, I-Z. But that's helpful because usually we're not so interested in what happens to a particular substance. Usually we add something to cause something else to be oxidized. Okay? So in our pools we put chlorine, not because we're interested in what happens to the chlorine, but because we want to oxidize the crap that's in the pool. So chlorine is an oxidizing agent. Right? So absolutely, that's exactly what happens. So all right. And then here's just a review of oxidation numbers. We said elements, pure elements that are neutral are 0. Ions, they're equal to their charge. O is usually -2. H is usually +1. Halogens are usually -1. Okay? So same thing pretty much that we do with charges of things. From those basic rules there, you can pretty much figure out any oxidation number just by arithmetic. Okay?
When is H not +1?
If it is a hydride, if it is sodium hydride, that is Na plus H minus. So if you've got a metal with hydrogen, it's a hydride. So if you've got H with a nonmetal, like HCl, that's H plus. But if you got a metal and then hydride, that's H minus. So strong reducing agent, turns out. So, alrighty. So we are back to balancing. Nice bookend to the course here. We started out with balancing very early on, like week 1 in the first semester. We are back to balancing because when we do an oxidation reduction reaction, balancing starts to get a little complicated. So, but thankfully we have a nice stepwise way of doing it that makes it not so hard, and if you practice it a couple of times you will be totally fine. So here is an oxidation reduction reaction. Okay? The main complication here is the O's in that. Okay? We can't just balance this with coefficients because we got extra O's. Okay? Sometimes you'll have extra H's and OH's and things like that. Okay? That's what we have to deal with. So we're going to divide it into 2 half reactions. We're going to have the oxidation just as itself and the reduction just as itself. Okay? So if we had Fe2+, what does Fe2+ just become? Yeah. That is 1 half reaction. So then the other half reaction is MnO4 minus becomes Mn2+. Okay? So every oxidation reduction you can split into those 2 half reactions just by tracing the elements. Okay? So that's what half reactions are. One of those will be an oxidation. One of them will be a reduction. We'll be able to see that very clearly here in just a second. Okay? So, and then what we do now that we have it separated into half reactions, we balance each half reaction. Okay? So balancing now is not just coefficients. It's a couple other things. So why don't you rewrite the Fe2+ makes Fe3+. Right down here, and we will balance that. It is, this one's actually already balanced in terms of atoms, but what is not balanced here? The charge is not balanced. Okay, so elements are fine. Don't have to worry about O, don't have to worry about H, but we need to balance the charge. So what can I do with electrons? Where can I put electrons? So I'm going to say +1 electron. Okay, so then that one is good. Put a little check by that. If we have an electron as a product, is that a loss of an electron or a gain of an electron? That's a loss of an electron. So loss of electron means this is the what? This is the oxidation. If you break it up into balanced half reactions, you'll be able to instantly see if it's an oxidation or reduction based on where the electrons are. Okay? So that was not so bad. We have a little more work to do with the other one, with the reduction half reaction. Okay? So let's go in order. Let's start with elements that are not O or H. I think we are okay on elements that are not O or H. So here, let's put a little check mark here for elements. That's just regular balancing with coefficients. Okay? To balance O, we add water to one side or another. Okay? So how will I add water here to balance this?
+2 water?
Plus
Or 4 water?
4 waters to the left or the right? Okay, so Mn2 plus 4 waters. Okay? Because there are 2 H's, but there's 1 O in each water. Okay? So that gave us 4 O's on the left and 4 O's on the right. So then we are good for O. All right. but now we got H's. So we add H plus to take care of those. So MnO4 minus then what? Yep. How many H pluses? Yeah, 4 times 2. Got it? Then we got 8 H's on both sides. Check mark H. Elements are good. O is good. H is good. Now what? Charge. And be very careful with this. Add up the total charges on each side, including the coefficients. So this coefficient 8 goes with that plus. There's a single minus there. So what's the total charge over on the left side? Yep. Like something like plus 7. Over here, water doesn't change anything. It's just the manganese. That's plus 2. There we go. So what do you think, Gort? What should I do with plus electrons?
More electrons on the left side?
We need more electrons on the left side because electrons are minus. We need to get that left side to plus 2. So we need 5 electrons. Yep. Everybody see how that works? MnO4, 1 minus, 8 H plus, 5 electrons. Check mark for. There we go. Let's just call that pluses and minuses. We are plus 5 on the left and, we are plus 2 on the left and plus 2 on the right. No. Okay? So now we have 2 balanced half reactions. Okay? This is the reduction half reaction because we are gaining electrons. Electrons need to be fed into this one. Okay? We're not losing electrons, we are gaining electrons. Okay? All right. Next step is to look at the reaction, the electrons. Because remember, both of these half reactions are part of the same full reaction, and whatever electrons are lost by one have to be gained by the other. So we need to multiply one or both half reactions by an integer so that the number of electrons are equal in both of the half reactions.
So we'd be multiplying the oxidation reaction by 5.
Yes, because we need 5 of those oxidation reactions to produce the 5 electrons that are needed by the reduction. Correct? So, say something like this, times 5. In order to get those to match up. So that is now 5 Fe2 plus and makes 5 Fe3 plus and 5 electrons. Now they match. Well, let's look at what step 4 is. Let's add the 2 half reactions together. Cancel those electrons fully. Okay? I'll take your word for it, but that you're right. That is the logical step to be doing here. Okay, so 5 Fe2 plus And then all the other reactants from over here, the manganese MnO4 minus, and the 8 H pluses. And you can write the 5 electrons if you want. Or on the other side, 5 Fe3 plus, 5 electrons. I've been underlining coefficients. Mn2 plus, 4 waters. But look at what happens. 5 electrons, 5 electrons. And after canceling those electrons, that is your balanced redox reaction. Okay? So the complication comes from adding O's, adding waters to get the O's to match, adding H pluses to get the H's to match, adding electrons to get the charges to match, making both of the half reactions equal in electrons so that when you combine them, the electrons cancel. Okay? A balanced redox reaction will not show electrons in it. It'll be understood that the electrons lost by one half reaction are gained by the other half reaction. Okay? So, let's continue on with that same one from before. If you're just told to balance it, or if you're told that it's a neutral or acidic solution, that's just what you do. Okay? The only time you have to do something different is if you are told the reaction is in basic solution. Okay? Just sort of one little extra step. What we have to do is add OH minus to both sides to get the H pluses to cancel. It's a little acid-base neutralization that happens here. Okay? So take a look at what would happen here. I'm actually just going to do it right down here so you don't have to rewrite. Okay? If basic no, I'm going to run out of room. Let's rewrite it. It's not a big deal. We have plenty of room on the other page to do it. So let's rewrite right here. 5, do it right here above A. 5 Fe2 plus MnO4 minus 8 H plus arrow 5 Fe3 plus Fe3 plus Mn2 plus 4H2O. All right. So how many OHs do we need to put on each side? 8 OHs. So let's just write them right here. Plus 8 OH minus plus 8 OH minus. Okay. Combine H plus and OH minus to make waters. So what does that mean we're going to have? Right here, yeah, going to have 8 waters on that side. And all these other things, we had 4 waters and 8 OH minus over here. Right. So what happens, what do I mean by cancel excess H2O?
So take the 4 out from the right side.
Yep.
Or subtract 4 from both sides.
Yep, subtract 4 from both sides. That's the best way to look at it. Okay. So then we can rewrite if we want 5 Fe2 plus MnO4 minus 4 H2Os 5 Fe3 plus Mn2 plus, no H2Os, and 8 OH minus. So, like I said, you only have to go through that extra step right here at the end if you're told that it is in basic solution. Okay. We essentially added enough hydroxides to get rid of the H pluses, because there will probably not be H pluses in our reaction if it's in basic solution. Okay. They will be just neutralized by the OH in the solution. So we do that, we neutralize them, we make water. Okay. We add the OHs to both sides of the reaction, so we're not actually changing anything. Okay. It's just like algebra. You can do the same thing to both sides of an equation. Okay. So if that's the case, then we make waters out of the H pluses that cancel. We'll then end up probably with waters on both sides, so you can subtract them so that you only have waters on one side. Okay. Whichever are present equally on both sides will cancel, and then you're just left with whatever else you have. So it was 4 of those waters that canceled from both sides and left us with the other 4. Okay. So let's give it a try. Here is a unbalanced redox equation. What usually works best is to divide your paper in half for the 2 half reactions. So start with 1 half reaction over here, the other half reaction over there. Go through and balance them both, just like we did, sort of stepwise. Balancing goes elements, then O, then H, then electrons. So start by just sort of tracing the atoms to get 2 half reactions. You trace the manganese, for instance, and you trace the sulfur. So draw a line. Draw a line. Write this one here. Just rewrite your first one. Yep. With an arrow, and show the product that's related to it. Yep, there you go. And then do the other reactant and the product that's formed from it. So, well, no, you'll still start with a reactant. Yeah, there you go. Oops, SO3, 2 minus. Does that make sense? Mm-hmm, yep. But we have steps in our balancing that take care of that. Okay. Everybody get the half reactions separated out at least? It has to be per substance, so it has to be SO4 2 minus.
Okay.
Yep.
Oh, on this one, how can we just...
Because that was a substance listed. Yep.
Okay. Yeah.
You're just pretty much choosing the things from the reaction that are related. You'll have 2 pairs that are related to each other, and copy them exactly as they appear. Ding ding. Yep. Oh, no, use water. Yep, there you go. Yep, make sure to add waters to get your O's balanced. Then add H pluses to get your H's balanced.
So I added 2 H2O.
Yep.
Those
Okay.
cancel, right?
Yep.
And
Yep.
I added 1 electron to this side to get that.
You have to do the electrons at the end.
Oh, okay.
Yeah, you have to go in order.
Okay.
So yeah, start with just your waters. Yep. Then add H pluses to one side or another. Yeah. So keep those 2 H2Os there.
Okay.
Yeah, and then get the H's right over
Yeah,
there.
that's
Yep.
fine. So it had to be 2 H.
Yeah. Use the coefficient too. Yeah. Okay. Did you get it?
Electrons on this side.
Okay, so add up. You get 2 minus over here,
There'd be 1 minus.
uh,
no, there's
2
two,
minus
so
and
it's
2 plus, so
0.
that's a 0. So you need 2 electrons over
that
here.
side.
Yep. I think you need your water over here, because SO3 needs another O to make SO4. Yeah. Otherwise, you'll end up with your H's on the same side. Okay. Yep. Oh, here, make sure to copy MnO2. That's going to change your waters.
Okay. So then we just have 2 waters.
Yep. Mm-hmm. Yep. 2 waters. And then 4. Yep. Okay. Did anybody figure out electrons for the first one yet?
Yeah, you gotta add 3 electrons to the left side.
Yep. Because it looks like 3 plus total and then 0 on the right. So we can do 3 minuses. Okay, that's good. We did elements, we did O's as water, we did H's as H plus, we did charges as electrons. Anybody get electrons for the second one?
2 electrons on the right side.
Yep. That's right, because we got 2 minus over on the left here and 2 minus and 2 plus. So we need 2 minus over on the right. Okay. So what's next? We have to multiply. So how are we going to do that? What am I going to do on the left one? Yep, we got to do a times 2. And on the right one, yeah, I got to do times 3. I got to do a least common multiple situation with the electrons there. Okay. Times 3. 3. 3. 3. What's 3 times 2? 6. And if you did that right, what should you be able to say about your electrons then? Yep. Excuse me. Okay. I'm just going to combine the whole thing first before we cancel it. As you get to practicing, you can sort of cancel based on what's existing. But I'm just going to quickly write the whole thing. 8H plus 6E. I'm going to color code here. 3SO3 2 minus 3H2O 2MnO2 4H2O 3SO4 6H plus 6. Okay, let's start canceling. The electrons cancel. Okay, what else? Some H's cancel. Right? 6 H's cancel. Right? Leaving us with how many over here? Okay, so I just usually do it like that. Okay, what else? Yeah. How many H2O's cancel? 3 H2O's cancel, leaving us with 1 there. So that cleans it up pretty nice. 2H plus 3SO3 2 minus 2MnO2 H2O. That is balanced for acidic or neutral conditions. That was a lot of writing. And honestly, I wrote this out more than probably you would have to, but I wanted to show it specifically stepwise. For instance, you on that one up on the left over there, you'd probably just be able to add the water and the H plus and the E minus right to the equation. Okay. But I wanted to show it stepwise here. Okay. What about basic solution? How many? Both sides? Okay. Over here, those become what? H2O's. And if we already have one H2O over there, what happens? one of them cancels. So really, it's just remembering the sequence. If you go out of order, you'll probably know it because you'll never get it to work. So if you run into a big problem with this, first, easiest thing to check is if you went in the right order. Then next thing to check is your arithmetic. Because if you do 2 times 3 equals 5 or something like that, or 3 times 3 equals 6 or something, if you do something like that, it's not going to work either. So, but otherwise, it's just basically clerical work from there, if you know what the procedure is. So, questions about those? I know that's the most fun thing in the world to do, but